Hello everyone and welcome. Today I'm going to talk to you about Markov State Models. So let me share my screen with you. So Markov State Models are a kind of tool that can be used in machine learning. And today we're going to talk about how we can set those up and how we can run those. And we'll be working on a lab that will go along with that. So let's put up our slideshow and display this so you'll be able to see. All right, so this is what we'll be talking about today. First, we'll have a brief look at what Markov State Models are, define what they are, and get a sense for how they work. Then we're going to talk about random walks, which is an important background information to understand how Markov State Models work. Next, we'll proceed to MSM theory, and finally, we'll proceed to some examples from the literature. So let's take a look at Markov State Models. What is a Markov State Model? It's a class of models modeling a long time scale dynamics of molecular systems. Oftentimes we're going to use molecular dynamics simulations in order to actually see what it is that they're going to do. And sorry, I'm just looking for my pointer here. And these are going to be useful then for modeling dynamics of a system when we're going to have a situation where we don't have information about the prior step. All we're going to know about is the current place that we're in, and then going to ask the question, where is the system going to go next on the basis of some probabilities. So this is an example of how we might have some various states in the system, and then here's also some others. States in the system, and the idea is that there can be some transitions between these various states. Now what the states would represent could be some sort of a conformation in a molecule, for example. And so then over some time, the idea is we would transition between those different states. Sometimes it will stay in the same state, and sometimes it will progress to a different state. And so we're going to try to understand what those probabilities of transition would be and where it can transition to. So that gives us the idea of how Markov state models are comprised. It's a set of conformational states, which are these circles here, and then there would be a matrix of transition. So this is a very simple model where it's just proceeding from one position to the next, but we could have a matrix of transition probabilities that could include forward and backward transitions. So for example, if the system were also proceeding in the backward direction, we would have a forward transition, then a backward transition, and so forth for all the different states, which would then comprise a matrix that would allow transitions between a variety of different states, and those would have some probability that would be learned from, say, for example, a molecular dynamics simulation. So a more formal way to look at what this is given by this here in probability theory. A Markov model is a stochastic model used to model randomly changing systems. And that's why we're going to take a look at the random walks, because random walk means it's going to progress in a direction based solely on random selection. So we're going to have random selection, but random selection with a weighted probability, which is the major difference between a purely random walk and what we're going to have here. And this is also going to assume a future state depends only on the current state, not on the events that occurred before it. And that is called the Markov property, which we will look at in more detail. So then let's go take a look at random walks, so we can get some appropriate background information. So random walk in 3D, this is something you might have seen before. You may have encompassed this in the physical chemistry class, or maybe you've talked about dispersal of a dye in a fluid or Brownian dynamics. All of these things are appropriate places where you may have talked about a random walk. So consider a particle in 3D space. Suppose you take a step in a random direction for a step size of 1 unit. So then on average, the step size the step should basically average out to be 0. However, that is not always the case, and we can actually, in fact, get displacement. So this figure over here is just showing three instances of a random walk, a blue one, a red one, and a green one, and each of the particles then is going to be sampling the space by randomly selecting between 4 different directions to walk in, north, south, east, or west, and then also to step up or down, because that's what makes it be random in 3D. And so then we see that they end up in different places. So to make things a little bit simpler, let's consider a random walk on a number line. So if we consider the integer number line as depicted here, we're going to start at 0. So then we have a fair coin, meaning that it has 50% chance of heads and 50% chance of tails. Then what we can do is we can work out where we would be at after some number of coin flips. So the rules are very simple. If you get heads, you're going to move 1 integer to the right from the 0, and if you get tails, you move 1 integer to the left. And then the big question is, where will the marker be after n flips? So we can actually work this out. So let's say we'll take n equals 5 just to get something that's reasonably countable. And then what we can do is we can in fact actually work out all of the possible flips that could happen for 5 coin tosses. Okay, so the first flip could either be heads or tails, and then if we had heads on the first flip, then we could have either heads or tails for the next one, and so forth. And so what this does is it generates this binary tree where we could actually work out the heads or tails. And so based on, so you see here what we have is the outcome total coin flips, right? So this example is what if you roll all 5 heads, right? So, and then all of the other possibilities are worked out here. So these are the outcome sequences. And so from those outcome sequences, we can work out how many times we would land on each of these various positions on the number line. So in the maximum displacement, we could go 5 steps to the right or 5 steps to the left. Those would be the maximum displacements we could have, and then there would be some other displacements that are in the intermediary region. So what we can do then is we can actually look to see how many different ways there are in order to get to those. So since -5 and +5 are going to be the extremes in the coin tosses, they're going to be the most rare, and those can only occur in one way, either getting 5 tails or getting 5 heads. We can also get -3, -1, 1, and 3. You can see that in fact it would not be possible to land on the even numbers with 5 coin tosses, but clearly the way that is the most populous is the -1 or +1 at 10 ways to get that, which we can see from the enumeration down here. So these are of course the positions that it ends up in, working it from the combination of heads and tails that we have here. And so from this, we can gain information about what the expected displacement would be. So it would be most likely that it's +1 or -1 from the starting point of 0, but it could be -3 or +3 or -5 or +5 with decreasing probabilities. So that's useful for us to have in mind as we think about the Markov model theory, because basically what we're going to have is, like we had those positions on the number lines, now what we're going to have is some states, and we're going to be making moves between the different states, just like we did the coin toss to make moves. But instead of having probabilities of 50-50 every single time, what we can do is we can have an attribute of different probabilities for the different states. So let's take a look at MSM. It's a mathematical framework for the analysis of time series data, often but not limited to high-dimensional MD simulation data. The next point of this is the creation of an MSM is going to involve decomposing the phase or configuration space occupied by a dynamical system in discrete states, and then we're going to have a transition matrix between those. So we also need to keep track of whether we're in equilibrium or not. And so this is going to become an important property of the Markov State models. Now, In a molecular dynamics simulation, we're typically trying to study an equilibrium property, and we run a number of tests in order to ensure that that case is true. However, MSMs can be used to study the equilibrium exchange, that is, as we're going from one state to another state. However, it's not necessary to have to do that or to do it in equilibrium. We can choose either way to use the Markov State models. They can also be used to study non-equilibrium processes. They can be used to study the kinetic events to capture a transition from one state to another. The Markov property, coming back to that, is this idea that we don't necessarily have to have information about what happened in the past in order to figure out what will happen next. So when we are going to step between one state and another state, that the only information that is used in order to figure that out is based on the current position that we're in and the probabilities that are associated with that. The probabilities are going to solely depend on the current position and the probability to transition to another state. So because of this, that means that long-range effects are not going to be captured by the Markov models. So let's consider the lag time and the problem with overcounting and the self-transitions. So suppose we have a molecular dynamics simulation. So this one is a very simplified version, and these are representative of taking some sampling of the conformation of a protein over the simulation. So we have only 15 states, and I've left this space in between them, not to indicate that it's a different time, but just to separate them out visually. So the green ones are all a particular conformation, the blue ones are another conformation, and the purple ones are a third conformation. So when we're going to do that, we're going to have our Markov state model, and let's say that there are 3 states. Now these states are color-coded to match what it is that they're supposed to be talking about. So the green ones are going to tell about the green state, and the blue ones about the blue, and so forth. And so we're going to have a series of arrows connecting them all together. So in a Markov state model, it's possible to transition between all the states. So all transitions are possible. However, not all of them are in fact actually observed. So for example, in this model, we never observe that a purple transitions to a green. We observe green to blue, and we observe blue to purple over the course of the simulation. So let us suppose that we in fact wanted to just count how many transitions we saw between the different states. So now what we have here is we have green goes to green, goes to another green, goes to another green, goes to another green. So these are the self-transitions. So that's 4 self-transitions where a green is followed by another green. Right here, this one is a green to a blue transition. So now this is going to populate this arrow with a 1, going from the green state to a blue state. So we have 1 transition. Now we have blue to blue to blue to blue to blue, which is 4 transitions of blue to itself. And then we have 1 transition from blue to purple, which gives us this one here, and then 4 transitions in purple. So that gives us this Markov state model that we see down here. Now, let's just step back for a moment and let's ask the question, is a transition between a state and itself interesting? Well, not really. And so, in fact, actually, you could change that. Imagine that our sampling frequency were doubled, that we took time steps generating more snapshots in between here. So that's in fact not going to give us any more interesting information, but you can see that the transitions between green and blue is going to still be the same, but the number of transitions between the green, for example, would double. And so those are not important transitions because it's not actually saying that anything happened, that it went from this state to another state. It's saying it was in this state for this number of this amount of time. So because we're trying to convert time, that is the frequency of the snapshots, into the counts that we're using here, there's a problem that can arise because you can have too many self-transitions. And so what we really want to do is make the counts be more important than that by changing the frequency at which we're going to sample the trajectory. And so that is what gives this idea of lag time. How much time is going to be between your samplings? Can we get a better picture of what's actually happening by changing that lag time? So let's consider the situation where we could just count at a lower frequency. So here's an example where I've counted with an increased lag time. I increased it to 5. So if we counted every 5th one, I would take a look at this one, and then I would skip 2, 3, 4, and the 5th one, and then I would go on to the next one. So now we would have a green to blue transition. So I would only get a count of 1, and all of those not very important transitions between the green would be skipped. And then we could take a look on the same time scale here. So you see what will happen is then we'll get a transition between the blue and the purple. And so this gives us a bit more of a meaningful kind of a picture of what's happening here. So we're going to increase the lag time to decrease the meaningless high frequency transitions that we see. That's the self transitions, and we can adjust the lag time to capture the meaningful transitions in the simulation of interest. That brings us to the probability matrix. And so as we've been just doing these hand calculations, it should bring to your mind the idea that the transition matrix is going to be dependent upon the lag time that we pick, right? Because we used the same simulation and we got a different matrix out of it. We got a different Markov State model. So the transitions are going to be defined by the probability matrix. So that is P and tau, which means that it is going to be a function of a specific amount of time. That's our lag time. And so these probabilities should obey balance. So the detailed balance is basically for the equilibrium state. Now, if you are not working in the equilibrium state, then this will not hold. But if you are working under the auspices of an equilibrium Markov State model, then this in fact should hold. So what this is saying is that essentially the forward transitions have to be equal to the backward transitions overall. Now, what this doesn't mean is this does not imply that it would be necessary for the exact probabilities or the exact counts in the forward direction have to exactly equal the number of counts in the backward direction. It just means that the net number of going forward must equal the net number of going back. That is essentially the definition of equilibrium. So the pi I is going to be the stationary probability of state I, and by stationary, what we mean here is equilibrium. So the Pij is going to be the probability of transitioning to state J conditional on being in state I. So the overall probability to go forward is going to be equal to the probability to go backward. If it's not a preserved system and it's not at equilibrium, then this won't hold. And so if in fact it's not an equilibrium, then it means there's an external force on the system, which you can use Markov State models to model. But if it is an equilibrium one, then this is what you should see. So coming back to that lag time, we've shown how we can kind of just get a concept of what it might be. But I want to bring up this idea of the Goldilocks principle. Now, the Goldilocks principle is actually not really a very scientific thing. It's just a sort of a mnemonic that I like to use to help me remember how we should choose that lag time. And we'll talk about how we could actually calculate an appropriate lag time in a moment. But the idea is that you should have a lag time that's just about right. And so this ties into a fairy tale story that we read to our children about Goldilocks and the Three Bears, and it's about a little girl and a bear wanders into the little girl wanders into the bear's house and tries out something that's too big, something that's too little, and something that's just the right size, which is baby bear's stuff. And so this happens with eating porridge and various other things, pieces of furniture in their home. And what happens is eventually Goldilocks discovers that baby bear is has a bed that's just the right size for him, and she falls asleep in his bed, and the three bears come back and discover Goldilocks there. But the Goldilocks principle basically means choosing something that's not too big, and not too small, but something that's just the right size for what it is we want to do. And that's the idea of the Goldilocks principle. So if we increase the lag time to be too long, well, let's say we made the lag time be 15. That would be as long as the simulation. We would go from green to purple, right? That would be too large because we would miss out on the transition of green to blue and then blue to purple. So that would be too big. And as we talked about, if we had a lag time of 1, that would be too small because we would have too many self-transitions. And so what it is we want to do is we want to adjust the lag time to capture the meaningful transitions in the simulation that we're trying to use. So we can estimate an appropriate lag time, which is based on the idea of implied timescales. So what your lag time is going to depend somewhat on the kind of simulations that you're doing, and also somewhat on what is a, quote, interesting property, right? So there are various motions that molecules undergo, and they may occur on different timescales. So you need to select a timescale that's going to be appropriate for the timescale that you need to select a timescale that's appropriate for the thing that you want to see. Now, you may not know what that is before you get started, and that could be part of your research question. And so when that's the case, then we need to ask some questions about how could we figure out what an appropriate lag time is going to be. So the implied timescales, or ITS, is the timescale of events captured by the Markov State Model, determined by the time over which the snapshots for counting are taken. That's something that we've seen on a couple of these toy examples. The TI is going to approximate the decorrelation time of the ith process. That is, what are the distinct properties that happen, and we don't want to look at the transitions between the same state and the same state all the time. So we want to have a decorrelation so that when we take our time step, whatever we decide that's going to be, that we will in fact have the opportunity to resolve some interesting event rather than always just stepping through the same thing over and over again. Markov State Model transition matrix can be deconvolved into the eigenvalues and eigenvectors. So this is something you would learn how to do in linear algebra. And then the eigenvalues can be used to compute the TI value according to this formula shown here. Another thing we may wish to do is validate the Markovian property, and that is done using the Chapman-Kolmogorov test. So the idea here is that the probability transition matrix for some transition frequency tau times a constant k, or the estimated lag time k times tau, or k is an integer greater than 1, is going to be equal to the concept of the probability matrix raised to the power of k times tau. Now, essentially what this is going to be telling you about is that if you look at an event on a shorter time scale, and then you try to compute what your probability matrices are, if you change that time scale to, say, an order of magnitude larger, we should still be seeing essentially the same picture. That's basically what this is saying, so that it's going to be robust to the selection of our lag time. So another way to look at this is how frequently we sample. So if we sampled at, so I'm thinking about our toy model, if we sampled at 5 versus at 4, we would see essentially the same picture. Not exactly, but essentially the same sort of a picture, which would be different from if we had a lag time of 1 where the self-transitions would dominate. So we're looking for those self-transitions to stop dominating our count and get on to transition times that are going to allow us to actually see something interesting. And so you could, in fact, use this test here, the Chapman-Kolmogorov test, to verify that that, in fact, is true. So now that we've had a little bit of chance to talk about some of the theory behind the Markov State Models, I wanted to take a moment to actually show you a couple of Markov State Models from the literature. So this example is from a pentapeptide, so that means it's a fragment of a protein, and that fragment is being put together in a length of 5 residues, and that is going to undergo an MD simulation. And during that simulation, there were a variety of different conformations that were observed. So there were 5 conformations, and they are exhibited here by the backbone representation of this backbone. So, and then they have been superimposed. So we see that they underwent these various conformations, and we have the important transitions between them highlighted. Now, again, I'll mention the fact that all transitions are possible. It's just that some may be very, very small and so are insignificantly seen and may be chosen to be omitted, which is what we're looking at here. So we see that there are 5 substates which have distinct conformations, and that there are transitions between those. And the difference in the conformations we can see because of the way that they are aligning. So Markov state models then can capture these dynamics by showing the transition probabilities between those different conformational states. I also like to tell you a little bit about Markov state models that we've been using in our lab. So we're actually using them in a slightly different way. So instead of starting with just a plain molecular dynamics simulation and inferring directly as we've talked about here, we're doing something a little bit different. So we're doing cluster analysis in order to figure out what the substates are. So when we do the cluster analysis, this is for the PDZ protein, which is an allosteric protein. We get out 5 different states. Now, it's just a coincidence that there are 5 between both of the models that I'm showing you. In fact, there's not really a way to know how many substates you might have, although it does seem that for this kind of analysis, a number in that order is appropriate and interpretable. So that's why we have this. We're also using a number of statistical tests to verify that the correct number of substates has been chosen. So these are the 5 substates, and we were able to compute the, and so we're in fact using a series of different molecular dynamics simulations. And so what you're looking at here is the transition probabilities between the different states for a variety of different MD simulations based on the liganded state of a PDZ protein undergoing allosteric activation. So we can see is that there are different states that are populated under various situations. So that's for our simulations. And so what we're really interested in looking at here is what kind of information we can get out. So these are the populations. So for example, the blue is our free protein, and in the blue simulation, which has just the protein in it, there are 2 states, A and C, that are populated, and the populations transition between them. So we can see then out of our entire simulation that this is about 65 and this is about 35. And so we're repeating those populations inside of our states. And then what we're doing is we're taking a look at our counts between those states. So here we see that there are 3,121 times that this transitioned into itself, and 406 times, 404 that it went forward from state A to state C, and from state C back to state A is 406. And so we can see that the probabilities for going in the forward direction and the backward direction are almost exactly identical, which is going to then verify our condition of being in equilibrium. We can also look at similar things for the green one. So we see that the green is also partitioned between 2. And again, the forward and the backward probabilities written here in the green are also almost identical. So that means that it's transitioning between them. And most of the time, however, when it is in one of these states, it does transition back and forth between itself. And when we have an allosteric effector involved, it's going to change the simulation to a different conformation, and this is what introduces the substates D and E, which pertain only to the liganded state involving the allosteric effector. So we did not know that would happen before we got started, and so our procedure, in fact, actually learned that information and reported that back to us. So what we can see is that we have the red one, with which is the allosteric effector by itself, is partitioning between 2 different substates and is transitioning forward and backward with exactly the same number of transitions. And the black one here, the black bars are partitioned between the same substates D and E. And so what we can see is that there is some forward transition and backward transition between them. This one maybe not totally in equilibrium because we see that the forward is smaller than the backward. But once it gets stuck in a particular state, it does tend to stay there. And so this gives us an idea about the lag time of our system and the appropriateness of the choice of how long we've taken it. So we can, in fact, actually pull out some of the transitions that are going to be meaningful so that we do, in fact, get some counts for the probabilities that we've used here in the forward and the backward transitions so that we can interpret these results. And so we're using this Markov State Model then to do things such as understand how allosteric effectors are able to interact with proteins and cause them to have a different conformation. So then that brings us to our summary. So we have Markov State Models. We had a first look at them to get an idea as to what they actually are. We talked about random walks because that pertains to how a decision is made about what next step it's going to take, which is somewhat similar to a random walk. We then looked through the MSM theory to get an idea of how the transition matrices are actually made and the considerations of lag time. And then finally, we took a look at two major examples from the literature. So then, this is an excellent reference and recommended reading that I would encourage you to have a look at if you have additional questions about Markov State Models. So with that then, I hope you enjoyed our chat today about Markov State Models. I have some exercises prepared for you to actually work on making some Markov State Models. So I would encourage you to go to the Moodle site and to download and work on the guide sheet we have prepared for you today. Thank you very much.